I would manage to my foot. I'm terrified. I'm not trying to buy it. Oh, that's 30 dollars. Yeah. It's comforting.
Cool. Perfect. So welcome all to the upcoming colloquium. It's the last one before Thanksgiving break. So, but lots to look forward to today. Speaker today is Dr. Cromartie. She did her undergraduate work at the UNT Chapel Hill, and she was also at the time a NSF RDU scientist out at Arecibo, where if you've seen the movie Contact and you know Jodie Foster's hut in that movie, she was there discovering.
I lived in that hut as well, in the cabin.
Indeed.
That specific one. Yeah.
And discovered a large sample of millisecond pulsars. So you can imagine our speaker today with the headphones on, listening to radio signals in the same way. Not completely accurate, but it did sort of prove to be a formative experience and took her on to her PhD at the University of Virginia. And from there on to an Einstein Fellowship at Cornell. She's now at the Naval Research Laboratory. But if she looks very familiar to you, it's probably because of the NANOGrav results that we had up here in the classroom last semester, which featured her work very prominently as the chair of the Pulsar timing relay group within NANOGrav. And she'll be telling us about that work today. So thankful.
Exactly. Thank you so much. I really appreciate the introduction. And thank you so much for having me. I'm very happy to be here. Having thankful right before Thanksgiving. It wasn't planned, but it was nice. Anyway, I'm going to be talking about NANOGrav. I'm going to be talking about detecting gravitational waves with pulsar timing and a smattering of other things. So an extremely quick introduction to millisecond pulsars and how we time them. So as we know, massive stars, they go through their stellar evolution, and a subset of them will end as neutron stars, right? The most massive progenitors, or maybe not quite the most massive progenitors, because people like to call these failed black holes, right? And so the end product of this evolutionary process is a neutron star. But we didn't have observational evidence of these objects until in the late 60s, a graduate student named Jocelyn Bell-Burnell was doing an unrelated low-frequency radio project and saw this ticking coming from one specific part of the sky. And the signal was so regular that at the beginning, they actually called them LGM for little green men, because it looked like it couldn't possibly be of astrophysical origin. It rather had to be human-made. It was a joke, of course, but what this ended up being was a spinning neutron star, or a pulsar. And so I do like to mention that Dr. Bell-Burnell was snubbed by the Nobel Committee. The prize was given to her advisor and department chair for the work, but she never really expressed any anger about that. But it is, I think, worth mentioning. So pulsars. These are rapidly rotating, highly magnetized neutron stars. They beam they beam radiation out of their magnetic axes as they spin. And so they don't actually pulse. They're more like a lighthouse. They're beaming radiation and they spin around. And so every time the beam crosses your line of sight, you see that as a tick. You see it as a pulse. And so pulsars don't pulse, but they do spin very rapidly. They're about city-sized in diameter. They have masses between 1 and 2 solar masses, but that's a little bit contentious, and we'll talk about that later. But the ones I'm going to talk about today are a very specific part of the population called millisecond pulsars. And so these are spinning at millisecond rotational rates, so kind of unbelievably fast. And somewhat counterintuitively, they're actually quite old, because they've been spun up to these rates so fast due to the accretion of matter from a companion, conservation of angular momentum. They're going to get spun up very, very fast. In the process, that binary orbit circularizes. And so these end up being some of the most kind of consistent, good pulsars for doing what we call pulsar timing. They're very, very steady. They're very predictable. We only know of about 400 of these millisecond pulsars. We know of more than 4,000 regular young pulsars. And typically these are thought of as radio objects. So we do observations. I primarily work at very low frequencies, so between 300 megahertz and a couple of gigahertz. There are also observations at very high frequencies, so in gamma and X-rays. We're going to be focusing today for NANOGrav work on radio observations, but both of those kind of extreme regimes are really where we think of studying pulsars. Okay, so why do we care about pulsars? They're very cool intrinsically, but they're also useful tools. And so this is pulsar timing. Pulsar timing is the process of creating a model where you're accounting for every single rotation of one of these neutron stars over very long time periods. And so basically you want to create a model where you can say, I know exactly when the nth pulse from this pulsar will arrive in many, many, many years. And so it would be really easy if the pulses actually just came at a perfectly regular interval, right? It wouldn't be hard to make a model that predicts the time of arrival. But in reality, there are a lot of sort of things going on that make the pulses arrive not on time. These things range from the motion of the Earth, obviously, right? We have to normalize everything to the very center of the solar system. It can be the interstellar medium causing problems with dispersion. We'll talk about that a little bit. If it's in a binary, you have to account for the delay induced by the binary orbit, all kinds of things that you have to take into consideration in these models. And so what you actually end up coming up with is more like what's on the bottom, which is, a very well predicted model, right? It's a model that predicts the time of arrival well, but it's not very regular. So the plot on the left kind of shows you what we're actually dealing with in terms of pulsar data. So we are not looking at individual pulsations from pulsars, right? We're folding up many, many rotations in order to get a clear signal. And so these pulse profiles are not, this is not one rotation of the pulsar, right? This is an integrated profile. And that is what stays very steady over long periods of time. So I mentioned some of the things that can dictate the times of arrival of pulses. I have a nice little plot on the left that can show you sort of what we're looking to do when we're timing a pulsar. If your model is sort of accounting for all of these different parameters correctly, all these different astrophysical factors that impact arrival times, you'll get a very nice scatter around zero, right? You don't see a lot of residual structure in these timing residuals, right? This is just the difference between the predicted and measured time of arrival of pulses. But if, for example, you have a small error in the spin down rate in your model, it's going to induce this exponential growth over time, right? If you have something like an error in the position, you're going to get yearly cycles that are just sinusoidal. If you have proper motion, that error is going to grow in time. And so anyway, you can see all of these different kinds of residual structure in your timing residuals. And it's a good indication that there is something missing from your model. So this is a very kind of toy view of what's actually happening during pulsar timing, but I think it illustrates kind of all the different things that we have to take into account. It's worth mentioning that pulsar timing is extraordinarily powerful. So you can see on the bottom right, the period of this pulsar, J1713, that's how well we know the period, right? Which I think is just phenomenal. And this isn't even up to date. Don't tell anyone, but it's from several years ago. But the precision with which we can measure these times of arrival rivals atomic clocks. And so these are really kind of natural astrophysical clocks. And I think it's so neat that we can use them to do other astrophysics. Okay, so I haven't even defined what a PTA is yet. It's pulsar timing array, spoiler alert. But pulsar timing array work needs great precision. And so we have to start thinking about what we call the noise budget. And there are lots of things that come into play. One, kind of obvious one is white noise, right? There's radiometer noise, there's intrinsic jitter in the pulsars, but there are also several different kinds of sources of red noise, some of which are chromatic and some of which aren't. So there's intrinsic spin noise in pulsars. These are kind of long-term variation due to not super well understood changes intrinsic to the pulsars themselves. There's also dispersion measure, right? So the interstellar medium disperses pulses with a 1/observing frequency squared relationship. And so you can see, if you tried to integrate down the figure in the middle on the top, it's obviously just a cartoon, but the pulse gets dispersed like this, right? The low frequency light is going to be coming way later than it should. And so what you have to do is line all of these up in order to actually integrate down over your whole band and get a clear view of the pulse. You wouldn't get that if you didn't de-disperse the data. And so that's a really big problem as well. And the way we go about modeling the changes in dispersion measure over time is a source of real complication and frustration for us as high precision millisecond astronomers. Okay, PTAs. So we know in EM astronomy, right, normal electromagnetic standard stuff, there's something like 20 orders of magnitude over which we can observe. And depending on what kind of instruments you're using and where on the spectrum you're looking, you're going to be able to probe different astrophysical processes. This is kind of a beautiful thing about the field that we're in, right? And so you can see all these different views of Jupiter depending where in the spectrum you're looking. But we're not talking about that today. We're talking about something analogous, which is gravitational waves. So about 100 years ago, a lot of you have heard this story, so I'm really sorry. I know everyone's probably rolling their eyes, but about 100 years ago, Einstein had GR. There's a prediction from GR that says that accelerating masses are going to make waves propagate out in space, right? These are fluctuations in space-time, and they are propagating out at the speed of light. And people worked really hard to figure out how you can actually detect that. And so, in the 60s, there were these interesting experiments, a resonant mass detector looking for small changes due to gravitational waves. And then there were some predictions once pulsars became a thing, and especially once millisecond pulsars came around in the early 80s, that you could use pulsar timing to try to look for gravitational waves. And so I wanted to show you just really quickly, we think of gravitational waves, in the classical sense as having plus and cross polarizations with this strain measurement being very important, H. It is the change in path length over some nominal path length that is induced by the gravitational wave. And so you'll see that strain value in a few different places, but you can kind of look at it as that little fluctuation, that little deviation. So the first indirect detection of gravitational waves was actually in a pulsar context. And so there was a neutron star pulsar binary where they were able to measure the loss of energy in the system through gravitational waves and show the coalescence of the system over time. This is the Holtz-Taylor binary. They were awarded the Nobel Prize in the 90s for this work. And it wasn't a direct detection, but it was exactly consistent with the prediction from GR. You can see that in the plot on the bottom left. And then obviously in 2015, LIGO had the first direct detection of gravitational waves. These are sort of tens of solar mass sources. You hear the amazing, now iconic chirp from the coalescence, right? And you can see the very iconic plots on the right. I think we all at least somewhat know about this discovery, but it was obviously an extremely big deal to be able to kind of directly probe gravitational waves. Okay, so this is the analogous picture of the spectrum, right? And actually, if you include sort of CMB level things, you get about 20 orders of magnitude in gravitational wave frequency space as well. And just in the same way that you're probing different things by looking in different parts of the EM spectrum, you're looking at different things in the gravitational wave spectrum as well. And so, LIGO is sensitive to very high frequency or relatively high frequency gravitational waves. These are from lower mass objects, accelerating, right? The binary coalescence of tens of solar masses. LISA kind of lives in this in-between space. They have some sensitivity to extreme mass ratios of the two objects. They have sensitivity to slightly more massive events, but definitely sort of in this complementary place. And then what I'm talking about today are pulsar timing array experiments. And so we are sensitive to very low frequency gravitational waves, nanohertz, as in NANOGrav. gravitational waves. And so our sources are totally different. These are supermassive black hole binaries, and it's during the in-spiral phase of their evolution, right? And so our signal is caused by much more massive objects, but they're also way lower frequency. And so the time scale of our experiment is going to be quite a bit longer than for Lisa and LIGO, for example. Not the lifetime of the experiment, but like what we're sensitive to, what we're trying to get sensitivity to, takes a much longer time. So the detector itself is a collection of pulsars. They're all relatively local, all within our galaxy. They're all over the sky, and we time each of them individually, right? So we observe with our radio telescopes each of these pulsars that can be very precisely timed. I'm about to start swinging the stick around. I don't want to do that. So if we can time these all to very high precision, we know that if there are slight path length changes, that a gravitational wave is passing through. And the signal that we're actually sensitive to is an ensemble signal of all of the supermassive binary black hole mergers going on all over the universe, right? But at its very core, what we're looking for are little path length changes between us and the pulsar. And that is going to be, it's not just the path length changes, it's correlating those small little changes, which induce small little changes in the timing residuals, correlating those between all of the pulsars in the array. And so what we're actually looking for is an angular, the angular pairwise correlation in these very, very small deviations in the timing residuals. And so here's kind of a look. If you watched the event, you already saw this video. I'm not subjecting you to the whole thing. This just gives you an idea of what the actual array looks like, right? It's this collection of here 68 millisecond pulsars. They're all relatively local, but they're distributed all over the place. But it's funny to think about, right? Because we're not a ground-based detector. That really is our detector. It's just all of those pulsars. Yes.
Is the absolute distance of each pulsar, does that need to be known accurately, or is it really just?
So it doesn't. It helps to have a good sense of it, right? And so for some of these, we have good proper motion measurements. For some of them, we just have constraints based on dispersion measure variations, or rather dispersion measure measurements. But no, it's not necessary to know the distance, although it would really, really help. And I think that becomes more relevant when you're talking about continuous wave detection as well. Okay, cool. Sorry about that. So our first goal in a pulsar timing array experiment is to detect that stochastic background of gravitational waves. We think that this is a roughly isotropic signal from all of those different coalescences of supermassive binary black holes happening all over the universe. A prediction of GR is this correlation that I was talking about. So as a function of angular separation between all of the pulsar pairs, there's going to be a certain amount of change in the arrival time induced by the gravitational waves. We call that the Hellings and Downs curve, and it gives us an indication of whether the signal that we're seeing is simply some excess noise process that doesn't, isn't correlated in any way between all the pulsars, or it's actually something that is affecting the pulsars systematically. And it has this very, kind of distinct quadrupolar correlation. And so that's one way we're able to pick out the Hellings and Downs correlations from any other effects that might be at play. Why do we do this though? The purpose of this is to study, primarily study how these galaxies grow and merge and form over cosmic time, right? Because this is really giving us a view of how the mergers proceed, what happens when they get to when the supermassive binary black holes get a certain distance apart from each other, how, what effects actually make them coalesce. And also things like the population of these supermassive black holes, what the masses are, how often they merge, how massive they are, things like that. And so these are all things we hope to get a handle on through these pulsar timing observations. And I'll also mention, in the future, we will gain sensitivity to things like individual mergers and maybe even more exotic physics. that I'll mention at the very end.
Question.
Yes,
Should I think of what is being seen as two single gravitational waves coming through space and time, or many at the same time?
it's you should think of it as many at the same time, sort of, although it's not at the same time, sort of implies that it's happening quickly, right? I mean, it's quite a slow process because it's quite a low frequency signal, but I think it's more accurate to think of this specific stochastic background signal as an ensemble, but we will gain sensitivity to kind of single gravitational wave sources, more easily modeled, I guess. Okay, oh yes, sorry.
Sorry, so intuitively, the Helling-Downs curve that you drew, I feel like so in my head, that looks kind of like a quadrupole, right? Is there a reason it doesn't look exactly like a quadrupole?
Yeah, this is a great question. So, and it's really hard for me to answer because this is not my area of expertise. It is not intuitive at all. I can try to struggle to explain it. I mean, I think one answer is that it's not actually the Helling-Downs curve should not be perfectly quadrupolar, and I think it's because it's something inherent to the gravitational waves themselves. But the other thing I think is that it has to do with the fact that there's some directionality, like our pulsars aren't just in like a, one spot or a specific well-distributed kind of cluster. I think there's some directional impact as well. I've never been able to explain this well though. And I apologize for that, but yeah. Yes.
I have a really naive question. Do gravitational waves get redshifted, like cosmological?
Yes.
That shift like into and out of your frequency range, or is it broad enough?
Yeah, but I imagine that, so we'll look at the astrophysical interpretation in a little bit. This is not my area. This is very much not my area. I imagine that is impactful, but I'm not sure if we have like sources that are right on the edge of being in our frequency band that could, that are like, if they were a little bit further away or something, they would not show up. I think that's probably not super relevant because the most booming sources are going to be a lot closer by. But yeah, I think that's a very good, very interesting question. Yeah.
Another naive question, but where does the gravitational wave background come from?
Yeah, so it's this, well, where does it come from? Like, so if it's due to supermassive black hole binary inspirals, it's because as these individual supermassive black holes are inspiraling, these are just accelerating masses, right? And they're big accelerating masses. And so those are going to create ripples. But then these are happening all over the place. It's not like this is just happening in one place, right? And so what you actually have is a bunch of different ripples coming from a bunch of different like droplets in your pond, if you want to think about it that way. And so the stochastic background, the ensemble signal is an overlap of all those different mergers going on at once. But it is kind of an open question, right? Because it's possible that the signal that we're seeing is actually due to some beyond the standard model physics, gravitational waves that were imprinted right after the Big Bang, like before the CMB. And so I can't say for sure, but we're fairly certain that this is coming from the binary black holes. So yeah. Okay. I don't want to get too far into the math here. I just sort of want to show you the spectrum that we're interested in, this gravitational wave strain spectrum. So you can see that sort of the quantities of interest here are the amplitude of the background, right? As well as the spectral index in this gravitational wave strain spectrum. And so if you assume that all of these binary supermassive black hole mergers are circular, and you assume some kind of mass distribution, then you get this Finney et al. 2001 result, which predicts a spectral index of 1330. And so that's kind of our benchmark, but we do search for other spectral indices, right? So if there's eccentricity or something like that, then that's going to change that value. You can look at the cross-power spectral density to get a sense of some of the other relevant quantities. So one of those is the overlap reduction function. And here, that's actually the Helling-Downs curve. But all I want to point out is that you can search for different kinds of signals, not just the quadrupolar correlations, but also a monopolar or a dipolar correlation. And so this lets you separate out different kinds of signals, right? A lot of people worry about like, how do you actually know that you're seeing what you're seeing? One reason is because the gravitational wave background is going to have a very distinctive quadrupolar correlation. If it's something like clock errors, which would affect all the pulsars, but it would be a monopolar signal, right? Just a time offset or something, that would show up differently. If it were a dipolar problem, like if it were a problem with our solar system ephemeris, which actually was relevant about 5 years ago, and I'll expand on that really quickly. So we are reliant on all of these solar system ephemerides that NASA puts out, right? Because we need to be able to transform to the solar system barycenter. And we have such sensitivity that very small changes in, for example, the mass or the orbit of Jupiter caused us to see an errant signal in our data. And so that, I think it's really cool, because I think it's very cool how sensitive we are. But that shows up as a dipolar correlation, right? It's like a not the same shape, I guess, as the gravitational wave background correlations. And so we really can pick out different kinds of signals, and we test for the presence of all these different sorts of signals. And so this is where, as we characterize this spectrum of gravitational waves in these low frequency regimes better over time, we can learn about the astrophysics in looking for things like, is there a really steep turnover in power law, right? That would show us about how the mergers proceed. Is there a lot of interaction with the environments? If we just look at the kind of amplitude, just the up and down change, it tells us about the rates of the mergers, all kinds of things that we can get out of better characterizing the spectrum. But this is, these aren't real data. This is just kind of what we're hoping to gain sensitivity to. And it's what we have now, but we can do this a lot better with more observations. Okay, NANOGrav. NANOGrav is the North American Nanohertz Observatory for Gravitational Waves. We're a physics frontier center funded by NSF. There are a lot of us. We've been growing very rapidly recently as well. There have been, people working on this for a couple decades now, which is extremely neat. The instruments that we work with most regularly are the Green Bank Telescope in West Virginia. We use the Very Large Array in New Mexico. Those are for high-ish frequency observations. We're very reliant now on the Canadian Hydrogen Intensity Mapping Experiment, which is a Canadian transit telescope that lets us get observations of our pulsars every day, which is extremely neat. And we were very reliant on the Arecibo telescope until its collapse in 2020, which was very difficult for personal and scientific reasons for so many people. But these are the instruments that we rely on the most. But it's not just NANOGrav in the game. We are only one of many pulsar timing array collaborations. We have colleagues in Europe, in South Africa, India, Australia, China, all over the place, all with their own amazing instruments, with each of which has pluses and minuses for observing pulsars. And so our goal in the IPTA is basically to bring together all of these different, very valuable pulsar timing data sets. And if we add them all together, the things we worry about are number of pulsars that we're timing, how long we've been timing them, and how well we can time them. And so putting all these data sets together increases our sensitivity to the background enormously. And so it's really hard because all of these data vary in so many different ways, but it really is something that's worth doing, even though it is a really hard task. So we're right now working on our 3rd data release in the IPTA, and an early version is actually going to be ready next month. Okay, so we had to do a lot of restructuring of our observing program after the loss of Arecibo. So right now, what our observing program looks like is 80 of our pulsars, 80-ish, are timed at the GBT, many of which are only timed at L-band. Some are timed at both L and 820. The ones timed at 820 megahertz are not visible with chime. The VLA gets us our slightly higher frequency observations, and then chime gets us those 53 with daily cadence. So basically, this is just to show you that we're going for monthly-ish observations of all of our pulsars, and we want to do it at 2 different observing frequencies where it's possible. Part of that is to get a better grip on kind of changes in the dispersion measure over time. So this is what our data sets have looked like. You can see the pulsars individually are on the x-axis. Time is going down from top to bottom on the left. There was a version of this plot that was animated during the announcements, so it might look familiar. But you can basically see, in 2013, we released our first data release. This was 5-ish years of data, 17 pulsars. It's grown until in the 15-year data set, which is what we published in June, there were 68 millisecond pulsars, and it was more than 15 years of data. It was like 16 and some years of data, but we don't talk about that. And so we truly are growing very quickly. We're trying to find new pulsars all of the time that are appropriate to add to the pulsar timing array. But it's actually quite hard because we have to be a little bit picky about which sources we use for timing.
Why is there a large gap around 2017?
Yes, it's a good question. So in 2017, those ones with the gap are ones that were only timed at Arecibo. And so there was an issue with a local oscillator. This has nothing to do with the collapse, actually. It was an issue with a local oscillator. And so for those of you who don't know, you have to have this sort of constant frequency thing that gets mixed with your signal. And if that is jumping around at all, it's going to contaminate your data. And unfortunately, enough of the data were contaminated that we really couldn't, we chose to just cut it all out because we weren't sure. Sometimes it was behaving okay, and sometimes it wasn't. We are actually working right now to try to mitigate some of this if we can, but we're not very optimistic about it. So it's just contaminated data, unfortunately. Yes.
Given that you were so precise with these timing experiments, and you mentioned even things like the ephemerides in the solar system having an impact, what about tidal forces on the Earth? Do they adjust site position enough that it actually throws off timing?
Oh, site position. Yeah, so I don't think so. We actually had some issue with this recently where we saw that the observatory coordinates in some of our timing software were like very, very slightly off. But on those scales, and certainly on the scales of tidal forces, it's not going to induce a super noticeable change. I also think that it doesn't induce like a quadrupolar, it's not going to induce a change that can get picked up in the gravitational wave searches. But yeah, that's a really good question. There are all those like little factors that you have to think about. Yes.
You know, it's more of like, what criteria you use to select the good?
Yeah, it sounds really hard, right? But what we're looking for are, primarily pulsars that don't eclipse. So there are a lot of pulsars in these highly accelerated binaries that we call spiders. So they have very low mass companions, mostly because they've been ablated away by the pulsar themselves. They have pretty, highly accelerated orbits, but they show more orbital variation over time that has to be modeled. The truth is that you actually can model that for some systems. Okay, you just add higher order orbital derivatives, right? But it's not ideal, and a lot of them show eclipses. So you definitely don't want that because you want to kind of maximize your observing time. You don't want any pulsars that glitch or have any of those kinds of unpredictable sort of things happen to them. We did have with one of our pulsars a sudden change of the pulse shape, which is still a big mystery. We think it has to do with some intrinsic change to the pulsar itself in the magnetosphere. It's probably not an ISM effect. Yeah, anyway, I'm happy to answer questions about that later, but basically just really easy to time, not changing very much over time, not requiring us to update our timing solutions to account for new effects, things like that. Yeah. Cool, I'll move on. So this is just same plot flipped over, and actually you can see the real times of arrival in this one, including like red noise and things like that. The 12.5-year data set was the one we released before this. It was in 2020. And so in that data set, we had 47 millisecond pulsars, and it was for the first time we were able to significantly detect a common red noise process in our pulsars. And so this is kind of a humming that was present, a noise signal that was present with the same spectral characteristics in all of the pulsars that we timed. And this was very interesting because, not really interesting or unpredicted, but it was cool. Because this is exactly what you expect to see sort of on the road to being able to see those quadrupolar spatial correlations that are the smoking gun of the gravitational wave background. And so we saw this common humming. We were able to put a limit on the gravitational wave background. And this was a very exciting result as well. Our colleagues in the IPA were seeing a very similar signal. And so things were looking very good. For the 15-year data set, we included 68 millisecond pulsars. So we got this big jump in the number of pulsars that we were timing, which was really great. I don't want to get too far into the weeds about how we do our actual pulsar timing. I skipped over all of that stuff because it's not the most engaging content. But there are two different ways sort of that we can do our pulsar timing, narrowband and wideband timing. Happy to answer questions about it at the end if you'd like. But wideband timing helps us reduce our data volume by quite a lot. And so we've produced both a narrowband and a wideband data set for the first time with 12.5 year. We did the same with the 15-year as well. We had data for the first time from the very large array in this release, which was very cool. It gives us access to a further south source called 0437, which is like a classic PTA source. So it's very cool for us to have access to it. And we decided to end the data set, obviously the collapse of Arecibo was a pretty obvious stopping point for the Arecibo data. We also, close to that time, switched over backends we used for pulsar timing at GBT. And so those were sort of the markers we used to denote the end of these data sets. I also won't talk too much of, oh yes, sorry, go ahead.
I was just wondering on the thought with all the different pulsars and stuff. I'm assuming colors are different. Is that right?
Yeah, that's correct.
If you don't know, it's totally fine.
Yeah, it's oh yeah. So a lot of these are, I think, orange and blue. It doesn't matter which one's on top. It's just the way it's plotted.
Oh, okay.
But those are the Arecibo pulsars. Purple is also Arecibo. That's like the high frequency at Arecibo. Green and blue is GBT. Yeah, that's a me problem. I apologize.
No.
You can see.
Sense. I just found the other one. There was only like one little patch of orange, and I got confused.
I should have made these a little bit more transparent. The pink is obviously VLA, and you can see that we have like the one VLA only pulsar, even though there is pink data here for some of the other sources. It's only a handful. Yeah. Okay, so this has been a big part of my life for the last 3 years, but I don't want to talk about it too much. There have been lots of exciting innovations in pulsar timing software. The kind of classic packages that were used, Tempo and Tempo 2, they are extraordinarily powerful. Many pulsar timers know them and love them / love-hate them. But it was really time that something got developed independently. And so there is PINT. PINT stands for PINT is not Tempo 3. It was developed totally independently, Python-based, it's modular, it's very cool to work with. But this is the first time that we were using PINT in our data release. But we were very careful. We produced data sets for both, using both pieces of timing software. They've been tested very thoroughly, and so we're not, that has been controlled for. One of the other reasons we wanted a pipeline is just because we are trying to expand the number of pulsars that we're timing by a ton. And so you really, it's not as simple as just kind of getting the data from the telescope and running it through and saying you've timed the pulsar. It's a whole kind of field unto itself, right? There are a lot of considerations. It takes a lot of time. It's very time intensive. And so we want to kind of deal with the things that we can deal with automatically as much as we can, but it doesn't give us an automatic front to back kind of solution for our timing. So if you're interested for some very strange reason, you can see the GitHub. It's called TimePal. Yeah. Okay, so one of the other reasons why I love pulsar timing array science is because it's kind of a greedy reason when I say it this way, but it gives us a data set that is just unprecedentedly sort of rich and valuable for other kinds of pulsar science, right? You're having monthly observations of dozens and dozens of pulsars over, decades. And so you can do some really cool stuff that you can't do by just proposing for sort of individual projects. So the thing that gets me most excited is trying to put constraints on the neutron star equation of state. So the neutron star equation of state, it's what is describing the relationship between pressure and density within the neutron star. We're especially interested in what's going on in the very deep core. It's supernuclear densities, right? Extraordinarily dense, very, difficult to impossible to test in laboratory conditions on Earth, although you can make some constraints that way. And it's very handy because you can translate this into observables, right? Into a relationship between the mass and the radius of the neutron star. And so you see all of these different, the different lines are different propositions for the equation of state. And the way we do this with pulsar timing is dead simple. All we want to do is find more and more massive neutron stars, right? Because if we find a neutron star of a very, very high mass, and the equation of state predicts that it would have collapsed before it reached that mass, then you know that it has to be adjusted in order to account for a pulsar that is that massive. And so it's a very straightforward way of putting constraints on the equation of state. So yes, go ahead.
All right, I have a quick question. So you were saying you want the equation of state for like the core specifically. How do you know that that's what you're measuring, if there are these different layers that might have to be equation of state from?
Yeah, that's a really, really good question. So some of the lower density parts of the parts of the picture can be probed in easier ways in laboratory facilities and things like that. That's not the only answer though. And I think that this would be much better answered by a nuclear physicist for sure. But yeah, by anyone in the room, honestly, who would like, go ahead. Yeah.
You don't know.
Thank you.
You told them the secret. Yeah, very good, thank you. Okay, so the way, the one way I'm talking about this, the one way of making very high precision mass measurements for neutron stars is Shapiro delay. So Shapiro delay is a post-Keplerian effect, right? It's what happens when the pulsar is at superior conjunction in its orbit with a companion. So when it's in superior conjunction, it's behind its companion along our line of sight. And so the deformation of spacetime by the companion is going to cause the pulse to arrive way later than expected. And it's a very sort of straightforward effect, GR-wise. We do have to assume GR in order to make these measurements, but that's not too bad. And what it lets us do, because the range and shape, these two post-Keplerian parameters that describe that delay, those are dependent on things like the mass of the pulsar, the mass of the companion, and other measurable quantities, things that we measure no matter what, as long as we're sort of modeling the Keplerian orbit. Measuring those post-Keplerian parameters lets us break that degeneracy between the mass of the pulsar and the mass of the companion, which means that we can get out the mass of the pulsar by itself. And so it's a little bit rare to be able to do this. It has to be a very edge-on system. It has to have, it has to time very well, which is kind of a strict enough constraint in and of itself. But in a very small subset of these highly inclined systems, we can get out a really good measurement of the mass. And so it's a very cool thing to be able to do. There are other post-Keplerian effects that have, similar sorts of ways of getting out the mass, but this is the one that we talk about the most. So there are a few examples of this, being a very fruitful way to do mass measurements. The first one, Demarest et al. 2010, was the first time we measured a 2 solar mass neutron star. This was a really big deal. The canonical neutron star always had 1.4 solar masses. We didn't really think they could get any bigger than that. And so to be able to precisely measure a neutron star of that mass, immediately puts some constraints on the equation of state, especially in sort of ruling out some of the more exotic sorts of proposals for the equation of state, things like hyperons and kaon condensates and all kinds of fun nuclear physics type things. Yes.
Do neutron stars always have the same equation of state?
Yeah, I would. Yes.
Okay.
Yeah, that's an interesting question. Yeah, I think the answer is yes. Would you like to answer?
Oh, we have the same what?
Equation of state.
Frequency.
Equation.
Equation of
Oh,
state.
yes.
Yeah, yeah.
Yes.
I was like, I think the answer is a definite yes, but there's, yeah. It would be very interesting if you had ones with completely different compositions somehow or something wild like that, but don't speak something like that into existence. Okay, so so this put a very immediate sort of constraint on the equation of state. In 2020, I led the team that measured the mass of J740 plus 6620 through the Shapiro delay technique. We measured its mass to be 2.14 plus or minus 0.09 solar masses. At that time, it was the most massive neutron star known. We did some work. I did some work with a colleague named Emmanuel Fonseca, who's been doing these kinds of experiments for a long time. We refined the mass down to it's something like 2.08 plus or minus 0.06 solar masses, so very much within the uncertainty region of the original measurement, but still quite massive. And so this was very exciting, right? This puts further constraints on the equation of state. But the other cool thing, yeah, okay, I don't go into this too much, and I am running out of time. But the other cool thing you can do is other types of experiments, and especially X-ray observations of neutron stars, pulsars, because they are looking at the photon bending going on near the pulsar, and they're sort of modeling the regions where the photons are coming from, and it's a very, very different sort of thing to do. They're able to measure the compactness of neutron stars, right? And so they're measuring a ratio of the mass to the radius of the neutron star. And so when we can very precisely measure the mass, that helps them put a prior on their mass measurements and therefore kind of better refine that radius measurement. And so this has had a bunch of really cool results. I don't really have time to get into it, but especially for O740 and a few other sources that are visible both in, with NICER, the Neutron Star Interior Composition Explorer, which is a X-ray telescope on the ISS, and in radio. There have been some very cool results from that work. Okay, so NANOGrav science results. I'm gonna fly through this. So this is only a limited selection of the pulsars the papers that we published in June. This was really exciting for us. So we did not call it a detection of gravitational waves. We called it strong evidence for a gravitational wave background. Happy to talk about the decision process that led to that if anyone wants. But it was cool, I think people saw that this was definitely a good step in the right direction for low frequency gravitational wave observations. It got a bunch of press and stuff. We had a good time with it. It was very exciting and humbling. And it wasn't just NANOGrav. All of our IPTA colleagues also published papers. I'll talk about that a tiny bit, but not as much as they deserve. Essentially, we're all kind of in agreement, and that's a really good thing. So I'll start talking about the dataset paper, the gravitational wave background search, and then some of the astrophysics and other things that come along with this work. So I already mentioned sort of the facts about the data set, I guess, and this is the part of it that I worked on the most. So some of the secondary science stuff that came out of the data set paper is pretty cool. We were able to do some updated mass measurements for a lot of our pulsars. 50 of the 68 pulsars are in binaries, and so that gives us an opportunity to do some cool post-Keplerian measurements. So what you see here, I talked a little bit about how we parameterize the Shapiro delay. And so here we are parameterizing it with the inclination angle and the mass of the companion. And so we do, instead of just having those as parameters in our normal sort of chi-square fit for our timing model, we can also, grid over these parameters and do a much more precise, much more informative kind of characterization of the mass that we're measuring. And so this gives us the relationships that come out of looking at this posteriors. And so this is very cool. One of the things is that the measurement for 0740, a lot of people asked about this. This was the 2.14 solar mass neutron star. This is not the state of the art for that because we use CHIME observations for the other studies. So that's not that interesting. 1614, the original 2 solar mass neutron star, had actually a very slight increase in the mass that was measured. I'm working on some stuff right now to try to figure out exactly what the relationship between how our red noise modeling and it, how it can impact our measurements of neutron star masses. It's not going to be a very large change. Like we know that our DM modeling can change our mass measurements by something on the order of like 1%, but I think we need to get a better grip on exactly how this relationship works. So there are also some indications of higher mass sources, sort of in the same way we got an indication that 0740 was pretty massive. These are very poor constraints, but they are interesting constraints, and so they merit follow-up by doing more observations of the sources over superior conjunction. And so you can see these are on 2 different scales on this left-hand plot. You can see some of the very precise measurements that we get with superior delay. There are also some extremely poor constraints. Some of these are for sources that we are doing follow-up for. The ones that only have one curve, one posterior curve shown are new. Obviously, they weren't in 12.5-year data set. And so you can just sort of see the change between the 12-year and the 15-year. About half of them, either the mass decreased or it stayed the same, and about half got bigger. And so we're not too worried about systematic effects. There's this conversation that happens a lot about, well, why do all these pulsar masses seem to be shrinking? And that actually isn't supported at all by this or any other work. It's just that we pay a lot of attention to the most massive pulsars, and there's some expectation that there's going to be some regression to the mean. So not surprising at all. Yeah, so this was very cool. We also look at sort of large studies of changes in astrometry measurements in our pulsars that I don't have time to talk about. But we do measure like parallax, for example, for all of the sources. And there are interesting things that, yes.
What does it mean, the blue bump in your pulsar? 0740, 620? Yeah.
This.
It's separate from your orange.
They have some overlap. Yeah. So the mass measured in this NANOGrav data set is slightly lower than in the last one, but we were able to improve the constraint. So it
looks like it's well over 2.1.
Yeah, so the constraint we had from the 12.5-year data was pretty poor. It's like very wide, yeah, but it was high. And so we're right around 2 right now. It's just a much better constraint. And with the inclusion of the nicer data, that actually bumps the mass up a tiny bit. And that's why we say it's not the state of the art, because that daily cadence data is much better for sampling more of the orbit. So it's yeah. Okay. Cool. And I should also say for those measurements, we did include like the projects that I led to refine the mass of the 740, like the supplemental Green-Bank telescope campaign observations are included in the NANOGrav data set. So in that way, we are including all of the GBT data we have. Okay, I don't have time to get into this, but I really, if you're really interested in this stuff, I highly recommend that you read this noise budget, this noise characterization paper, characterization paper. It really explains all of these different things we think about from start to finish with sources of noise in pulsar timing arrays. And it's very, very interesting. It's dense for sure, I'll warn you, but it's very cool. So it's sort of, part of what it's doing is justifying our use of red noise power law modeling. So to model the intrinsic red noise in our pulsars, as well as reproducing the sensitivity curve, sensitivity to gravitational wave background, that they're getting from the search for the background, which is work that's being done separately. So the noise budget's under control, and I strongly recommend reading this paper if you're interested. Okay, so the next paper is the sort of highlighted one, I guess I should say. This is where we present evidence for gravitational wave background. The plot that I have circled is just, you remember what the Hellings and Downs curve looked like. We're seeing something very consistent with it, and that's very cool, right? Some of the other things you're seeing, there's like the Hellings and Downs plot on the top right is really just for illustration. So in the actual analysis, we're not binning sources within different angular separations. This is just to illustrate what the Hellings and Downs result looks like. We also do very gamma, varied spectral index searches. We're actually finding that if you look at this amplitude and spectral index search plot, you see that we are actually a little bit off. We're finding a spectral index that it's a little bit steeper than gamma of 13/3, which is astrophysically interesting, but not like scary. It doesn't mean it's inconsistent with a gravitational wave background from supermassive binary black holes. It just means that we have to keep observing and get better measurements. So this was very cool, right? I mean, we were very excited about this. They use 67 of the 68 pulsars because they have a different limit, the time span of the pulsars that's included. The common process, that common humming that I talked about, that gained an enormous amount of significance over the 12.5-year data set. It was the first compelling evidence, we say, between 3 and 4 sigma, depending on if you're looking at the Bayesian or the frequentist statistical analysis of this being a, quadrupolar correlation, Hellings and Downs style correlation. So this is kind of the smoking gun that we've been looking for, I guess. Yeah, so to answer this question of how we know we're not wrong, I talked about the fact that the quadrupolar signal is quite distinct. We also search for, monopoles on their own, dipoles on their own. We actually find evidence that the one that's best supported is Hellings and Downs plus a small monopole, which is very interesting. And that's something that we have to kind of keep looking at, but it's very, very low amplitude. It's not something that is, it's not really a problem. It's just good that we can kind of isolate that signal, I guess. And it's something we have to keep an eye on as we keep going forward, obviously. So you can see also within the timing working group, we help them try to sort of control all of these different factors that we can, including observatory dependent schematics. And so they do their analyses with what we call split telescope data sets. So data sets made of only Arecibo data and only GBT data for those where the skies overlap, so you can see them at both observatories, which means it's, Arecibo's field of view is kind of small. All of this is consistent. We're not seeing any systematics that are standing out in one of the telescope's data sets over the other. So that was very good control. And the other thing is that our colleagues in the IPTA, that's not until later. Our colleagues in the IPTA are seeing things not necessarily with the same statistical significance. It all depends on, their data sets, their observing setup, all these things. But they are either seeing a common run process that is in agreement with the one we're seeing, or they're seeing Hellings and Downs correlations that are in agreement. And so this is a very strong piece of evidence that what we're seeing is real. Part of that is because all of our observatories are independent, right? We also use completely independent pipelines to do our analyses. And I think that that's a point that gets skipped over a lot. We're doing our analyses truly independently. And so it's really powerful in kind of making this picture, I think. Okay, so the analysis, or rather the interpretation of the actual search for gravitational waves is very interesting. I've already stressed this. We can't guarantee that what we're seeing is from a bunch of supermassive binary black hole in spirals. We have a hunch that that's what is making this background. The spectral index is, consistent for the most part with that. There's more of a turnover than what was necessarily predicted by a lot of models. And the amplitude is a bit higher. So we are actually thinking that this is a hint that either there are more mergers or they're happening more frequently, which is kind of cool. The turnover is also supporting the idea that there are more interactions with the host galaxy that are sort of causing the mergers to proceed. And this is cool as well. But, you know, we need to really emphasize here that the experiment has only started in this way, right? We are now thinking that we're seeing the background, but we really can't characterize the spectrum very well right now. And so we have to keep observing. We have to keep optimizing our observing program to improve our sensitivity. And we will get there, but it's going to take a lot of time. And so we're focusing right now on trying to improve our sensitivity and spectral characterization. Yes, okay, so beyond the standard model of physics, obviously really not my area of expertise, but I will say that there are all these different interesting sort of beyond the standard model models that predict primordial gravitational waves, right? So low frequency gravitational wave signal that's imprinted very soon after the Big Bang. And it can tell you all kinds of things like about inflation and phase transitions and cosmic string and all kinds of cool exotic phenomena. And they did a search using all of the different models that describe these things and what the gravitational wave signal would look like. And it's quite interesting because for some of these, the models actually explain the data a little bit better than the supermassive binary black hole data. But I really want to emphasize that that's not proof that what we think we're seeing is these primordial signals. It just means that we need sort of to keep observing. It's consistent. The signal right now is consistent with a lot of stuff. And so we have to just wait and figure that out. I see I'm out of time. Should I? Okay, super quickly. We're not seeing any anisotropy, and we're not yet seeing any continuous wave signals, meaning like individual supermassive black hole mergers. But we have to wait and observe more frequently in order to do this. So that's going to be a really big indication that what we're seeing is actually black hole mergers. IPTA colleagues are in agreement with what we're seeing, and right now we're working. I'm actually going to a busy week next month where we're all going to come together, work on getting our data all combined. It's an absolute mess. We love it. It's very cool, but it really is a headache of a problem. But I think it's really phenomenal. So what we're looking forward to, the GBT has an ultra wideband receiver that's coming online very soon. It's actually been through some testing. That's going to be really helpful for NANOGrav observations. The reason I'm at NRL actually now, I had several of the people I talked to today ask me about this, and it's a very good question. I'm continuing to work with NANOGrav, continuing to chair the timing working group, doing all that, but I'm also working on Fermi pulsar timing array work. And I think this is very exciting, but there was a result last year that basically showed that if you had a pulsar timing array made only of Fermi pulsars, so gamma ray data, single photon data, you can reach gravitational wave background limits that are similar within the next few years to what we can do in the radio. And this is really surprising. No one really believed that this was going to be possible. And it's very cool because gamma ray pulsar timing has a lot of benefits, like not being subject to dispersion measure variation. The interstellar medium is this big source of red noise for us anymore. And so we're working on getting this Fermi pulsar timing array off the ground, doing some joint gamma ray radio timing, really exciting stuff. I think it's super cool. DSC 2000, it's a proposed facility that's looking pretty good, pretty exciting. NANOGrav would get about a quarter of the time on that instrument. And so we're working very closely with that team. And that's all I've got. Sorry for rushing again. Thanks.
Questions, and David, we'll go to you first.
First of all, thank you. Very, very beautiful talk. Really cool. So I have two questions. So you said at the beginning of the talk that you want to add like something like to get to 200 something. So you guys in your collaboration have a sense of how much that would tighten the uncertainties on this measurement if it's real?
Yeah, so we think actually quite a lot about this optimization problem, right? There's some sort of back of the envelope, very basic kinds of forward predictions you can do to say we'll be able to characterize the gravitational wave background to this level if we add this many pulsars and time them for this long. It's just because there's this relationship between the number of pulsars, the sensitivity is linearly dependent on the number of pulsars, the time that you've been timing them, it's like a t to the 1/2, and then the sensitivity is a slightly less, or rather precision with which we can time the pulsars is an even slightly less important factor. And so those are very basic kind of predictions you can do, but it gets a lot more complicated when you think about things like, well, we don't just want to gain sensitivity to the gravitational wave background, we want to start gaining sensitivity to individual emergers and things like that. So it really turns into quite a mess. And then the observatories tell you that you can't just observe the entire time on the telescope forever and take away observing time from everyone else. So.
Yeah, you have a graph there of the strain H 10 to the minus 14, 10 to the minus 15. Go further. Yeah, but my question, yeah.
Oh, the amplitude, yeah, sure.
Yeah, but is that for single gravitational wave or, because I asked you earlier whether you're seeing an ensemble at the same time, you said yes.
It's for the ensemble.
So this is presumably individuals times square root of n, you see.
Yeah, yes, it's not, wait. But that doesn't, wait, individuals times the square root of n. I mean, it's for the combined signal.
It's sort of. How do you know, I guess, my real question, how do you know you're not seeing single waves? How do single
Oh,
waves
right.
or the waves overlapping?
Oh, I see. So if we were seeing a single wave, there would be a peak at some frequency in the gravitational wave spectrum, right? We would see that as some overlaid kind of single frequency. And we don't, it's a more level kind of spectrum. But yeah, we will presumably be able to see some of these, at certain frequencies popping out depending on the coalescence. Yeah. Sorry.
It's a good talk. The Fermi results are super interesting. I'm curious what makes that so as you get less uncertainty because of like all shapes. I don't know that much about what the Fermi observation cities.
Yeah, that's a great question. So one of the things you get with Fermi is that has been up so long, right, since like 2008, and you get essentially continuous data from all of those pulsars over that amount of time. A lot of pulsars are really quite precisely timed in gamma rays, and it's actually, I didn't go into any of this obviously, but the data is completely different, right? It's not some constant signal that you get in the radio, it's individual photons, and for some of the sources, you're like really grateful if you get one photon a day. And so the timing is a different process, but especially if you have a sort of a solution in the radio, a radio-derived solution, and then you apply it and line up all the photons correctly, you can get a really, really nice, you can get some very precisely timed sources. But the cadence and the length that they've been observed for are really helpful. We have also just access to a lot of pulsars. So, yeah.
Questions, Mickey?
So what are you said that you're confident but not 100% sure that this is a black hole binary merger background. What are the prospects, like what do you need to improve that confidence? Is it just the spectral of the
That's a great question. Yeah, so there are a few different things that are going to sort of bring this into view. One is just better characterizing the Hellings and Downs correlations, right? A better constraint on that would be more of an indicator. Another thing that we can see is anisotropy in the background. And so that's going to come with time as well, but that's not something that would be associated with a lot of primordial gravitational wave signals. And so the presence of anisotropy and especially the presence of individual mergers on top of that would be we'd be very confident. Hope, fingers crossed, we'll get there, but.
I was wondering with, you had mentioned with these, like monopole and dipole, sort of, for lack of a better word, because I can't remember what you said, but like errors or like problems that can arise. Like with the Jupiter one, for example, how easy to identify are these? Like how long did it take them to go, that's Jupiter? If my question makes sense.
That's a great question. It took us getting to a certain sensitivity level, first of all, for that dipole to come out. But you can see like the frequency of the signal, right? And so you can sort of deduce where it might be coming from in the ephemeris, even though it wasn't even obvious at first that it was the ephemeris. So we can do all of these sort of complicated things now with, we call it Bayes FM. It does a search over all of the different like kinds of little distortions in the ephemeris that you can make and things like that. But with the new JPL ephemerides, we actually don't see any difference at all. And so we're kind of good now. There's been some recent data from like Juno and things like that, which has been very cool to see that that problem has just like settled down. But it caught us by surprise. It was a stressful time. Yeah. Yeah.
So you said that if there's pulse shape ranges, that makes for a bad candidate pulsar. I would like to hear a little bit more about that, but also when you're looking at different observing frequencies, you're looking at different parts of the pulse, right? You're going to see a different pulse shape depending on the different observing frequencies.
Oh, yeah, observing frequency. Yes. Yeah, so I can, if we have time, I can try to give a good answer. So first of all, the pulse shape is not supposed to change with these millisecond pulsars, right? The average shape over time is supposed to stay pretty steady. We did have an incident where the pulse shape of one of our pulsars, 1713, just had a very quick, very short time scale change, and then it took this kind of slow path back to its original pulse shape. This matters because in order to actually extract our time of arrival measurements, we have to have a template for doing that cross correlation, right? And so if the template doesn't have the right pulse shape, we're just not going to be able to time the pulsar as well, or our TOAs are going to be a little bit off. What you say about the pulse shape changing over the observing frequency is an extremely good point. I teased wideband timing very quickly, but the point of wideband timing is that as our telescope, as our facilities improve and we're able to have more simultaneous bandwidth all at once, most pulsars have a fair amount of intrinsic shape change as a function of frequency, and that change stays constant over time, but it is there. And so instead of just saying this single static template is going to describe the shape over the entire band, we make now a portrait, a 3D template that shows the expected shape change as a function of frequency. And so that's what we want to use to extract our times of arrival. And a really great thing about that is that we no longer subband the data. We no longer split it into different frequency channels and take TOAs from all of those. We do a single measurement of the time of arrival and the dispersion measure. And so it increases or decreases our data volume enormously. I really ranted, I'm sorry. Hopefully that answered what you were asking, yeah.
Okay, I see actually multiple hands, so we'll finish up with Gordon. And I'd say if you have more questions after Gordon, come to dinner with the speaker.
Why do millisecond pulsars have smaller rates of glitches?
That's a very interesting question.
I guess the real question is, what is the level of glitches that occur?
Oh, so I think only one millisecond pulsar has been shown to glitch. I think the recycling process, a lot of things happen during the recycling process, right? A lot of things get evened out, the orbits get circularized and things sort of, they stop spinning down so quickly. I imagine that maybe if it does have to do with those vortices escaping from the crust, maybe there's something going on there. I don't actually know the answer, but there are essentially no glitches in these millisecond pulsars. So yeah.
Well, let's thank our speaker again.
Thank you.
Just a reminder, we don't have any colloquium next week because you're on Thanksgiving break. So see you the week after that, where we'll have Dr. Nicola Robin from Space House. See them. That was our end.
Hey.